Hi, I'm Marley Traeger. I'm a junior in aerospace engineering here at the University of Michigan, and I'm a research assistant for the Radiological Health Engineering Lab, where I first joined as a freshman through the Undergraduate Research Opportunity Program. This year, I've had the opportunity to lead a multidisciplinary team of undergraduate students, and we've been tasked with the creation of a multicopter drone for the purposes of radiological surveying, which we have named the Intelligent Radiation Awareness Drone, or IRAD for short. In this video, I'll be describing the work done for the development of the first iteration of the IRAD project and where we intend to go from here. The purpose of IRAD is to improve on the current methods of radiological surveying that we use today. Radiological surveying is useful to do routinely to build historical databases about what the normal amount of background radiation looks like in an area. That way, abnormalities can be detected, such as lost industrial grade radiotherapy sources or discovering radioactive geology in the form of abandoned mines that communities have built on top of unknowingly. Surveying is used to give rapid responders information about the very hazardous environment that they need to enter. And in general, more information allows people to make informed decisions. Radiological surveying is done all the time, but is relatively unknown to the general public. People often think that it's not done outside of agencies that directly work with radioactive sources, but it's generally required for the safety of large groups of people gathering, like during the Super Bowl, or when there's a known or suspected threat, like a bomb. But that's not to say that surveying wouldn't be an incredibly useful tool to others, but because radiation is a threat that can't be perceived outside of proper equipment, it's difficult to incentivize surveying to other communities when the cost is so high due to the large amount of specialized manpower needed and the general inefficiency of their processes. Right now, surveying involves the use of many people using handheld detectors and sweeping an entire area in some sort of grid-like pattern. This is inefficient and wildly resource heavy. The IRAD team is attempting to tackle this issue by surveying areas using an autonomous drone and driving the movement of that drone algorithmically. Using a drone allows for more maneuverability with the use of less people, and driving IRAD's movements using our lab's patented algorithm opens the doors for quicker surveying by not requiring every inch of an area to be directly measured in order to have a comprehensive map of what radioactive hazards are present. I'll be describing the general process of how this works, but I won't be getting into too much detail as the navigation algorithm is a largely independent project. Our technical approach involves using hobbyist-grade drone parts. This allows us to keep the cost of the drone down so that it can continue to be a learning experience for undergraduates. Essentially, they're allowed to fail and pick up the pieces because hobbyist equipment is easier to source and does the job we need it to. Also, due to the rising amount of drone hobbyists, there is a large knowledge base and community surrounding hobby drones, and we tap into help for them often. We are utilizing an open source control software called PX4 Autopilot that runs on a Pixhawk 4 flight controller. The autopilot takes care of all of the nuances of controlling IRAD and is used in industry and hobbyists alike. If a message is sent to the autopilot to move the drone forward, it does that. And creating our own control system is way beyond the scope of this project because we want to focus on implementing our algorithmic movement and get to surveying as fast as possible. We also have another computer on board IRAD that takes in information from our payload and handles the calculations for the algorithm. Figure 3 on the poster shows a high-level operation control loop of how IRAD will survey an area. First, a measurement of radioactive intensity called counts is taken by the payload sensor. Then that measurement, along with its GPS coordinates, is put into a database of every measurement taken during that particular survey. The algorithm uses a variety of statistical methods and predicts the location of a radioactive source and sends the new location via coordinates to the flight controller, which then moves IRAD to those coordinates, where it takes another measurement. This process is repeated until a certain tolerance of certainty is reached, usually in the form of a threshold count rate, where it says, "I've found a source." The idea is to create a map of discrete sources in an area to identify hazardous points instead of taking measurements everywhere in an area and using post-processing to determine hazards. Because the companion computer is on board the drone, IRAD can perform this in near real time, and the only limiting factor is how fast the drone can move from point to point. The largest hurdle integrating this has been the custom firmware needed to send messages between the flight controller and companion computer, but that has been successfully implemented by our wonderful team and is ready for integration in future iterations. The companion computer also handles the data collection for the sensors that allow for autonomous operation. There is a front-facing camera and a downward-facing LiDAR sensor. The camera sends data to the flight controller so the autopilot can anticipate and avoid obstacles with the collision avoidance software already implemented in the autopilot. Similarly, the LiDAR sensor sends data so the autopilot can perform terrain holding to ensure IRAD is always at the same height above the ground below it during the survey, even if it becomes uneven. This allows for two things. The sensing payload will always be within range to take measurements accurately, and IRAD will not disturb any potentially radioactive material that's on the ground by being too close to the ground. If loose dirt gets caught up in the air, we're not particularly sure if that loose dirt could be hazardous, and we don't want that to be an issue. The modular payload consists of two discrete modules. Only one will be present on board IRAD at a time. One module contains a line of sight radiation detector needed to complete the intended mission of IRAD that I've been describing. The other module has a Wi-Fi sensor to measure signal strength from Wi-Fi emitters as they are used as simulated radioactive sources. Because radiation and Wi-Fi are both electromagnetic waves, they both have decreasing intensity proportional to the inverse of the squared distance from which you measure them. This is the property utilized in the navigation algorithm, so a large irradiated environment can actually be simulated using Wi-Fi emitters and while using the Wi-Fi sensor payload. This allows IRAD to have a large-scale testing environment without having to acquire radioactive sources strong enough to be detected from several meters away or gain access to a very large irradiated environment that is hazardous. At this stage in development, the first iteration of the IRAD system is fully designed, which you can see on figures 1 and 2, and the wiring harness for essential flight hardware has been created and flight tested. Essential flight hardware includes the flight controller, power distribution system, motors, and communication systems. The collision avoidance and terrain holding systems have begun development independently and are beginning to prepare for integration, so future iterations of IRAD can be autonomous. As of the recording of this video, development on a second iteration has already begun. We plan on having more powerful motors and a robust frame to handle larger loads. This first iteration of IRAD was a bit of a trial run, and we didn't expect to be able to integrate everything due to weight constraints. With a more powerful system and more powerful motors, we will be able to lift the equipment needed for autonomous operation and generally have more reliability in the air. Currently, members of our team are training to get their Part 107 drone license from the FAA, which we will ensure our future flight testing is safe and beneficial to the project. It also gives us opportunities to test outside of the very controlled and small environments currently available to us. Once the second iteration is built up, we plan on completing lots of flight testing to characterize IRAD's movement in the air and seeing what it's capable of, as well as testing how the algorithm performs when it's controlling our drone. This project has been a great systems engineering challenge and a learning experience that my team and I have already been able to apply to other work. From here, this project will continue under the tentative title of IRAD Light, as our lab has purchased an industry standard heavy lifting drone for IRAD, which we hope to refine our search processes with. IRAD Light will continue to provide a development platform fit for incoming undergraduates as the RHE lab continues its mission to provide involved research opportunities in nuclear engineering and related fields.